Hey friends, welcome to another edition of Math That Matters. This is Logic and Argumentation. This is lecture 4. And again, I think you're going to love it because, well, I don't know, I love it. And why wouldn't you love it too? It's making you better, it's making you smarter, it's interesting, it's engaging, at least so I think it is. Let's go for it. Share my screen with you and see what happens. Right, here it is. Logic and Argumentation, day 4. We're going to talk about truth tables today. We're going to talk about showing or proving that two things that seem different aren't, or maybe two things that might seem the same aren't the same. We have to decide if saying something in a different way is actually, it retains the same meaning, or if it actually is something different. And so we're going to make what are called truth tables. We're going to take statements. Remember, statements are either true or false. They're not both, and you have to be able to figure out if they're true or false. So we're going to take statements like P and Q, two statements, and we're going to look at all the possibilities for truths and falses for the different statements. And then we're going to look at some sorts of combinations or negations of these statements. So if P is true, then not P is false. If Q is true and P is true, and I go over here and I look at this or statement, not P or Q, an or statement to be true requires that one of the two pieces are true. So I look over here at not P and I have false. Well, that's not good. But over here at Q, there's a truth. So all I need is one truth in one of these two things to say that the whole statement is true. So this is called a truth table. And it's going to be really instructive for us in determining whether two things that look different are actually the same or not. And then later on in the next lecture, we're going to look at arguments and we're going to test them to see if they're valid or not. So a lot to look forward to. Just to recap, conditional statements are these P imply Q statements. If P, then Q. So if I am sleeping, then I am breathing. But if we turn it around, we have the converse. If we flip the if and the then, if I am breathing, then I am sleeping. That would be the converse. The inverse is when we take and negate the if and also the then. If I am not sleeping, then I'm not breathing. And the contrapositive is if we turn the original statement around and negate both. If I'm not breathing, then I'm not sleeping. So remember those. That was in the last lesson. We're going to play with those a little bit today. The other thing to remember is that if you're negating a conditional statement, the negative of an if-then is actually an and statement. So if I say, if it is raining, then the ground is wet, and I negate that, if I do the not of that, that means the then is not following the if. So it means the if is true, it is raining, and the then is not true. It is raining and the ground is not wet. So make sure that you understand that to negate a conditional statement, you don't get another if-then statement, you get an and statement. And the only way an if-then statement can be false is when the if part is true and the then part is false. That means the then part is not following the if. So the if-then statement is false. That's going to be important for us. Here is a truth table for the if-then statement, P implies Q. If P, then Q. So I look at all the possible ways that P and Q can exist, the truth values. P and Q could both be true. P could be true and Q is false. P is false and Q is true, or they're both false. And then I wonder, in those different scenarios, what will I conclude about if P, then Q? Well, the way that I always think about this is I always look for the false here, because if I look for the truths first, I can get myself a little twisted up. You remember from the last lesson, there are things that are vacuously true. If a P implies Q statement has a false P, then the statement is true vacuously. And that's kind of tricky to the mind. But I can say to myself, P implies Q will be false when P is true, but Q does not follow. So when P is true, but Q is false. And when P is true and Q is false, this is the only scenario where that is the case, which means that P implies Q is false in that scenario and true in all other scenarios. want to look a little bit at the Alice in Wonderland story by Lewis Carroll. And he just plays with logic and characters and funny situations. And sometimes his logic is good and sometimes his logic is bad, but it's usually interesting and humorous. I like this quote from the Mad Hatter. Alice says, "I don't think," and he says, "Then you shouldn't talk." So we're learning to think in this unit, and that is good. It's a good thing. So I think this is a tea party, and they're having discussion, these different characters. "Then you should say what you mean," the March Hare went on. "I do," Alice hastily replied. At least I mean what I say. That's the same thing, you know." "Not the same thing a bit," said the Hatter. "You might just as well say that 'I see what I eat' is the same thing as 'I eat what I see.'" "You might just as well say," added the March Hare, "that 'I like what I get' is the same thing as 'I get what I like.'" "You might just as well say," added the Dormouse, who seemed to be talking in its sleep, "that 'I breathe when I sleep' is the same thing as 'I sleep when I breathe.'" "It is the same thing with you," said the Hatter. This is a dormouse in a person's hand. The dormouse is very, very small. So what can we do with all that? Are these the same or not? Why or why not? I guess explain yourself and then prove it. So you'll just have to explain it to yourself and think it if you're watching the video. But if I mean it, then I say it. Is that the same thing as if I say it, then I mean it? That might be a little bit tricky. If I mean it, then I say it. If I say it, then I mean it. Well, I'm kind of thinking in my head, there are things that I've said that I haven't really meant. Maybe I've said them in anger. I'm starting to think that maybe these aren't the same. Of course, we just read the Alice in Wonderland quote. And then they give us some other examples that make it seem obviously not true and ridiculous. If I eat it, then I see it, versus if I see it, then I eat it. Well, I'm looking at plenty of things right now that I'm not eating, so it doesn't quite seem to be the case. Most of the time when I'm eating, I do see what I'm eating. But how can we just eliminate the need to be intuitively smart? How can we eliminate the need for examples? How can we purely reduce all of this to logic and determine that these two instances really don't match each other, that they're not, it's not the same thing? And we can do that by assigning symbols to these statements. Let P be I see it, and let Q equal I eat it. And it really doesn't matter what P and Q are. What we're really comparing is if P then Q against if Q then P. "Put your hand on the firm ground of logic," replied the tiger lily, "and then you'll know." So what we need to do is we actually need to create a truth table, and we need to see if these things match. So here it is. We'll call this the converse test. Maybe some of you wear converse. There you go. So I look at P and Q. We just decided what those are going to be, but it doesn't really matter what they are. What we're really testing is if P then Q the same thing as if Q then P? We kind of think that it isn't, because intuitively we've got some examples that show us it doesn't seem at all that they're the same. But let's test them. So we take P and we take Q, and usually I just write true, 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 false, false, true, and false, false. These are all the possible scenarios for P and Q's truth values. And then I need to decide in those scenarios, when is P implies Q and when is it true and when is it false. So remember that P implies Q is only false when P is true, but Q is false. That's when you would say that statement is a lie. P is true, but Q doesn't follow it. So I look down here and I said, where is P true and Q false? P is true and Q is false right here. And that means the P implies Q statement is false here. And only false here, because in all other instances, we don't have a true false match. So false here, and then fill in the rest of the trues. Now, if we look at Q implies P, that will be true. Actually, let's look at that will be false when Q is false I'm sorry, boy, I should say that again. When Q is true, when the if is true, but the then doesn't follow it. So I'm looking for a true Q and a false P match. A true Q right here and a false P match leads me to say that Q implies P is false in that situation and only in that situation. Therefore, we have trues in the other three situations. Now, what we do to see if these two are logically equivalent is we look at the truth values in the different scenarios, and if the column truth values match from one to the other, then we say that they are logically equivalent. But you see, even though they match sometimes, true and true, right here, false and true do not match, and true and false do not match, even though down here, true and true match. So because this column doesn't perfectly match this column, we have now proven that these two things are not logical equivalents. If we would have gotten a perfect match in this column to this column, then we would have said, yes, these two statements, the column headings, are logical equivalents. Truly a good time. Well, one of the objectives of this course is to take arguments and try to understand if they're logical or if they're illogical. And another element of this course is to try to understand how the subject that we're learning, logic, relates to the biblical worldview and the biblical story. So I keep on reading in the book of John, and John is a master logician. And I keep running into all these sorts of things that we're learning about. So I want you to go into this story about Jesus healing a man born blind. I'll pull a few lines out of it, and we'll look at the logic of the man. We'll look at the logic of the Pharisees in the story. We'll look at the logic of Jesus in the story. But you might remember this is where Jesus actually spits on the ground and he makes mud and he puts mud on the man's eyes. This man born blind, and tells the man to go wash in the pool of Siloam. And he goes and washes, and suddenly he can see, which incites this great controversy because he did this on the Sabbath, and the Pharisees are looking to catch Jesus in doing something wrong, in breaking a rule. And of course, they've got all of these rules. One of the rules was that you can't work on the Sabbath, and one of the many ways to work was making mud. And if you spit on the ground, your spit might make mud with the ground. So you actually couldn't spit on the dirt on the Sabbath. Kind of ridiculous. And Jesus chastised them often for these rules made up by man that put a burden on the people. The Sabbath was supposed to be a blessing, right? And the Pharisees and the teachers of the law had made it a burden when it was supposed to be a relief. It was supposed to be a joy. It was supposed to be a connection with abundant life and full life and good life and relationship with each other and relationship with God. So here we pick up the middle of the story where the Pharisees are accusing this man or asking this man who did this, who healed you, and they're trying to catch Jesus, of course, and the man is just bearing testimony to the facts of the case. So here we are. What a surprise this is, the man said to the Pharisees. This is the man who was healed. You don't even know where Jesus comes from, but he healed my eyes and now I can see. We know that God doesn't listen to sinners, but only to godly people who do his will. It's interesting because what he's doing is he's actually repeating one of the teachings back to these teachers of the law that he had been taught. Yet who has ever heard of a man born blind that was healed and given back his eyesight? I tell you, if this man Jesus isn't from God, he wouldn't be able to heal me like he has. Some of the Jewish leaders were enraged and said, just who do you think you are to lecture us? You were born a blind, filthy sinner. So they threw the man out in the street. Of course, we're going to look at the logic of this man, and we're going to focus in on these yellow words. But I find it pretty interesting that he uses pretty powerful logic. In fact, he's using their own words kind of against them. And what do you do when you lose an argument? Well, what I learned in grade school was if someone beats you in an argument or makes you feel wrong or ashamed because they were smart, you beat them up. That's what I learned in grade school. But I think that that's probably not a good lesson. So that's kind of what the Pharisees are doing here. And I suppose you can beat someone up with power. You could physically beat them up, or you can beat a person up with shame. And I remember, actually, this is a side story, not intended for the video, but I remember being in high school, and there was kind of a bully in high school. He was a lot bigger than me. He got in a lot of fights, but I was smarter than him. And I just was trying to figure out, how do I deal with this? Because, in high school, when someone kind of challenges you to a fight, you think, well, I guess I'm supposed to fight them. Or back in the 80s, that's the way it was. But I didn't really want to fight this guy. In fact, I've never been in a physical fight in my life. And so I never fought him, but we actually had this conflict when we were freshmen. And by the time we were seniors, we were both in the locker room at one point, and we were alone. And it was kind of this intense moment. And I was thinking, boy, I guess maybe I need to defend myself finally. And rather than fight this person physically, I just tore him apart verbally. I reduced him to nothing with my words. And it was awful. It was terrible. It was sinful. And then we never talked until our 20-year reunion. So that was my senior year of high school. And then at our 20-year reunion, I actually went up to this guy and I said, I said some horrible things to you in high school, and I've changed and I feel terrible about it. And will you forgive me? And it was actually really cool because he did, and he was a good guy. It did take 20 years, and who knows how he felt based on the awful things that I said to him. That I don't know, maybe they kind of seem true. And I guess that's how you really can hurt a person with logic, is you can take true things about their life that are shameful, and you can elevate them to a place of pain. And I did that. But thanks to God, we reconciled 20 years later. Anyway, back to the story in the Bible. All right, so this man who had been healed by Jesus says, we know that God doesn't listen to sinners, but only to godly people who do his will. So he's saying, I think, isn't he? If a person is a sinner, then God will not listen to them, right? If God listens, then the person is not a sinner. Is that the same thing? That's the contrapositive, right? So we turn a statement around, we get the contrapositive, and we're wondering, when we just tested the converse of a statement, and we're like, that's not the same thing. So is this man using a good argument? That's the question. Is he saying something that is the same thing as what he's been taught, and he's just turning it around? Is he turning the words of the Pharisees back against them, or is he twisting the words in such a way that it doesn't fairly represent what he has been taught? If God listens, then the person is not a sinner. Is that the same thing? If a person is a sinner, then God will not listen to them? And of course, you can tell that here he's going here, but God listened to Jesus. He gave healing. He listened to him. Therefore, Jesus isn't a sinner. So he's making the case that Jesus isn't a sinner. So the question is he twisting the words of the Pharisees back against them logically, or is he unfaithfully twisting words just to kind of prove his point? Let's look a little further. He also says, if this man isn't from God, then he wouldn't be able to heal me like he has. So he kind of is saying, if Jesus healed me, then he was from God, and Jesus healed me, therefore he was from God. He's kind of actually using the contrapositive, or this blue statement is the contrapositive of the yellow statement. So basically, I took the if and the then, I turned them around, I switched them, and I knotted them. And then the question is, again, is that really the same thing? Can you do that? Is that legal? Is that logical? So I want to test a contrapositive against its original statement. In just a minute, let's finish the story, and then we'll do the test, and we'll see if this is good logic or bad logic. Is it okay to use a contrapositive and say that it's equivalent to the original statement, or is that a twisting of the words, a misuse of logic? We'll look at that, but let's finish the story. They throw this guy out, they bully him out, they shame him out, whatever. And Jesus goes up to him and says, do you believe in the Son of God? The man says, who is he? Tell me that I might place my faith in him. And Jesus says, you're looking at me. He's speaking to you. It is I. The man throws himself at his feet and worships Jesus and says, Lord, I believe in you. Also really interesting that the man is worshiping Jesus, and Jesus knows the Bible, and Jesus knows that you're supposed to worship God alone, and Jesus doesn't tell him, no, don't do this. Like Paul said, don't do this. There was many instances in the Bible where people are worshiped, and the faithful ones say, don't worship us. You're only supposed to worship God. And then people worship Jesus, and Jesus doesn't tell them not to, which is strong evidence that he is acknowledging his own divinity. And Jesus says, I have come to judge those who think they can see and make them blind. Interesting. And for those who are blind, like you were, I have come to make them see. The Pharisees standing nearby said, oh, do you mean to tell us that we are blind? And Jesus says, if you would acknowledge your blindness, then your sin would be removed. But now that you claim to see, your sin remains with you. So quickly, let's just look at Jesus's final argument here. If you would acknowledge your blindness, then your sin would be removed. Now, if the sin would be removed, that implies that it was already there, that they have a sin nature, that human nature is sinful, which we have talked about in this class. But now that you claim to see, your sin remains with you. So here we see Jesus saying, if you would admit it, then your sin would be removed. But you won't admit it, therefore your sin remains with you. Which I think is kind of interesting, because this is it looks like the inverse of this statement. The inverse is when you just negate the two statements. It actually is the inverse. And the inverse isn't logically equivalent to the original statement. We can test that and see that, just like the converse isn't. So it seems like Jesus is making what's called the inverse error, which is a fallacy of logic. But I think actually what he's doing is he's making what's called a biconditional statement, which we talked about in the last lesson. And he's really trying to say, your sin will be removed if and only if you acknowledge your blindness. The story is very interesting. We could talk more about it. We're looking at kind of sin and blindness and the comparables between the two, and having blindness removed and having sin removed, healing. So there's a lot to be said for this. And I hope that even looking at it in this kind of detail from this angle actually makes you understand and appreciate and enjoy what God is offering you more in Jesus Christ. All right, so let's take a look at what is called the law of contrapositive. I'll just tell you up front, the contrapositive and the original statement. So P implies Q, and then when you turn it around and you say not Q implies not P, those are actually logically equivalent. It's exactly the same thing to say one as saying the other, which is really a neat thing. So we're going to look at that and we're going to test that. The law of the contrapositive says P implies Q. If P, then Q is exactly the same thing as if not Q, then not P. And if you throw this into a truth table, you take P and Q, these are the two statements of interest, doesn't matter what they are. You run through all the different possibilities for P and Q, true, 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 false, false, true, false, false. And since we're going to be talking about their negations in more complex statements, these molecular statements, I'm going to put the nots here. So whatever P was, see, like it's true here, not P is false. Whatever Q is, not Q is the opposite. So whenever Q is false, we see true for not Q. So these are just the negations of what's over here. Then I go to P implies Q, which I've done twice already, even in this lecture. Where is P implies Q false? Where P is true and Q is false. So I look for where P is true and Q is false. And that is the only place P implies Q is false. All other scenarios, P implies Q is true. And then we look at this other statement, the contrapositive, not Q implies not P. Well, where is that false? That is false where not Q is true, the if part is true, and not P is false. Where is not Q true? Right here. And not P false, right here. So this is the row where we have a false under this heading. It's the only row where we get a true not Q and a false not P. That's the only place this is false. All the rest are true. And notice TT, FF, TT, TT. the column here matches perfectly the column here. And that is the test for logical equivalence. And so the argument that the man was making in the story, The Man Born Blind, to the Pharisees, when he was trying to use their words against them, when he turned their words around and negated them, and then made a conclusion based on that, was actually a, a logically legal way of doing it. So we see good logic being used by the man. And I think that's really cool and really interesting. What that means, though, too, this is the power that you have. You have the same power. So we might say something and it might be difficult to understand. It might be difficult to prove. So we have now a way of saying it differently. The contrapositive is a different way of saying something that's equivalent. So you can say it this other way and know that that means the same thing. And that new way of saying it might be easier to understand. It might be easier to prove. It might be easier to use in convincing someone else. So you, for free now, have the contrapositive of a statement. If the statement is true, then the contrapositive is true. I love it. So this is kind of a nice chart. You can pause the video and take a picture if you want. But this just shows, it's a truth table for the converse, which we already looked at, the contrapositive, which we already looked at, but it's also got the inverse. And what you can see is that the original statement, P implies Q, and the inverse, we got a T and a T, we got an F and a T. The inverse and the original statement do not match. So the inverse and the original are not logically equivalent. We also see, of course, we know that the original and the contrapositive do match, so the inverse and the contrapositive don't match. But what you do see is that the inverse and the converse match each other. So that means, here's a new rule, the inverse is logically equivalent to the converse. So if you want to say something this way, you can also say it this way because they're logically equivalent. In other words, Q implies P is exactly the same thing as saying not P implies not Q. You just turn them around and negate them, you get something that means exactly the same thing. Very, very useful, very interesting. Yeah, and as I mentioned, we're just looking to see if all these values match each other. If one column matches another column, then the column headings are logically equivalent. The converse and inverse are equivalent. The original statement and the contrapositive are logically equivalent. How about this? Show that the following are not equivalent. So not equivalent would mean that we make a truth table and we don't get matching columns. So let's think about this intuitively first, though. Not hot and not sunny versus not hot and sunny. Well, if I say it's not hot and sunny, could it be hot but not sunny? And this be true? And the answer is yeah. Yeah. If I say it is not both of these things, then simply it is not both of them, which means it could be one and not the other. It could be not both of them, but not hot and sunny means that it is not both, but it could be one or the other. It could also not be both, which is different than not hot and not sunny. That actually is a subset of this, but they're not exactly the same thing. And we'll show that they're not equivalent in just a minute. This is called De Morgan's law, which helps you learn how to negate and statements and negate or statements. Yeah, this is sort of what I was saying. So not hot and sunny is the same thing as saying not hot and sunny, or hot and not sunny, or not hot and not sunny. All three of those scenarios fall under the not, parenthesis, hot and sunny name for scenario. So it's three scenarios kind of packaged into one. It's not the same thing as not hot or not sunny, because that's only a part of the three different possibilities in this category. So what we see, and these are De Morgan's laws, we'll prove one of them in just a minute. We've been actually thinking through them without defining them, but here we're going to define them. Augustus de Morgan, famous mathematician, logician. So look at this. This is kind of interesting. So not, parentheses, P or Q is logically equivalent. If you see like an equal sign with a third equal, what that means is logically equivalent to not P and not Q. What's really interesting is you can almost distribute a negative through an or statement. You can almost distribute a negative through an and statement. But notice you can't do that because this or right here turns into an and. And this and right here turns into an or. So the not of an or turns into the and of the nots. Similarly, the not of an and turns into the or of the nots. That's kind of cool. So here is a truth table proving that De Morgan's law is true in the instance of negating an or statement. So not P or Q, we're going to show in this that it is the same thing as not P and not Q. So let's walk through it. We'll just say that P and Q are the two statements. Could be anything, but they have to be statements. So I'll look at all the different possible truth values for P and Q. True, 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 false, false, true, false, false. I always just do that the same time, same thing every time. This or, P or Q, requires for this molecular statement to be true, only one of the two has to be true. So I'm just looking for a true in one spot. I can have true in both spots and then I get a true here. I'm just looking for a true in one of these two spots. I've got a true there, so this is true. I get a true in one of these two spots, so this is true. But down here, I have a false and a false. So is P or Q true down in this scenario? And the answer is no, it's not, because they're both false. So I have to put a false there. No, we want to say something about the negation of this. And so we'll write not P or Q, but that's pretty easy because we have P or Q right here. So not that is exactly the opposite of whatever's here. So this is true, so that means this is false. This is true, so this is false. True, this is false. False, so this is true. These are exact opposites of this column. And again, what are we trying to do? We're trying to show that this, not P or Q, this thing right here, not P or Q, that it matches identically to the truth values in this other statement. And so this other statement kind of has a not P and a not Q as a part of it. So look at not P and not Q get written down. And you can use as many column headings as you need, though ultimately what we really are comparing is this column right here to this column over here, because those are the two things we're trying to show are logically equivalent. So not P is just the opposite of what P is. You look over here at P, P is true, so not P is false. Not Q, if you go over here, Q is true, so not Q is just exactly the opposite. Whatever shows over here for P and Q, true, false, we do the opposite, false, true. And then we have to assess the truth values of this final column, not P and not Q. Well, in order for this to be true, both of these things have to be true because it's an and statement. So I'm looking for a true combination. And I see it all the way down here, only in one instance, a true combination for not P, not Q. If they're both true, then I can say this and this is true. So I get a true down here. But in all other scenarios, comparing the not P and not Q, there's a false in one or both of the spots. So I have false values over here for the molecular statement. But now if you look at this, false, 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 true. And over here, false, 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 true. We have matching columns here and here. That means the column headings are logically equivalent. And this actually is a proof for De Morgan's law, at least the first part of it. And we could do the second part just as easily, but I'll leave that for you. Very, very useful and interesting. So anytime we can use a truth table to show that all the truth values for one statement match all the truth values for another, then we've shown that they're the same. And if they're the same, they're interchangeable. In the last lesson, I had this statement. We didn't prove it, but we're going to in just a minute. So it's kind of interesting because we have if P then Q, and then if we want to, we can actually change that and not even use an if P then Q statement. We can change that to a or statement. So if P then Q is the same thing as saying either not P or Q. And I explained that last time with a pretty good example, I think. So you could say, if you lift weights, then you will be strong. You can say that if you want to, or you could say either don't lift weights or be strong, right? Kind of comes from either don't lift weights or do lift weights. That's a tautology. But of course, this says if you lift weights, you'll be strong. So if you decide not to lift weights, go ahead. But if you do lift weights, then you'll be strong. So this is another logical equivalency that we can now prove with a truth table. Oh, and we did use that in an example from the last homework. So if something, then something could turn into either not the first thing or the second thing, right? Because if it's not blue, either it's not blue or it's blue. But if it's blue, then the triangle, if the square is blue, then the triangle is green. So we can use that logical equivalency to either say what's in italics right here or to say part E. They're exactly the same thing. They mean exactly the same thing. So you can use them interchangeably. But let's prove it. So let's make a truth table showing that if P then Q is exactly the same meaning as not P or Q. So I've got P's, I've got Q's, I've got not P's, I've got not Q's, and I just filled in all the different possible things that they could be. True, 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 false, false, true, false, false. And then all these are just the negations. They're the opposites of their counterpart. But what I really care about is looking at P implies Q against not P or Q. Well, let's see. P implies Q. This is like the not the eighth. It's probably the fourth or fifth time we've looked at P implies Q. The truth values of P implies Q. This is only false when P is true, but Q is false. P is true, but Q is false right here. And so that is the only scenario where P implies Q is false. In all other scenarios, P implies Q is true. It's either true directly or it's true vacuously. So I always look for where is it false? Where is the conditional false? And the rest is true. How about this statement? Not P or Q. Well, I'm going to look at the not P column. And I'm going to look at the Q column. And it's an or statement. So I'm looking for one of these two things being true. All it takes is one of the two to be true to say that not P or Q is true. So let's see, not P or Q. I'm looking at these two things. Oh, I've got a true one right there. So I'm going to put a true over here. Not P or Q. They're both false, actually, right? That means this not P or Q has to be false here. Not P or Q. Well, they're both true here. So that this statement is true. And then down here, I have at least one of them is true, and that's all I need. This one's true. This one's false, but this one's true. So this is true. Now you can see that the truth values true, false, true, true, and true, false, true, true match for these two things, which proves that they are logically equivalent. So saying this is the same thing in meaning as saying this. It might sound way different, but it means the same thing. And that's what we're looking for. Now, sometimes you get multiple statements in what you're trying to prove. So that's going to be tricky because if you have three statements, P and Q and R, and you want to look at all the different true or false values, that's actually going to require 8 different rows, which is a very large truth table. But you can still do it. It just takes more time. This actually is a truth table that is proving this, this argument that there's an arrow, so I'm going to read this as if then. If P or Q, then R is the same thing as saying if P then R and if Q then R, which I think is pretty interesting. But it sort of makes sense over here because you're like P or Q leads to R, but P or Q is true if you just have one or the other. So it's okay if you have P true and Q false, you're still going to get to R. It's okay if you have Q true and P false, you're still going to get to R because the OR statement allows for it. And if they're both true, no problem, you get to R. So P can get to R and Q can get to R. And you can see that the mapping on the truth table shows that the left side of this equivalency right here has all the same truth values as the right side of the equivalency. So saying what's over here means exactly the same thing as saying what's over here. And you might rather say it this way, but you might rather say it this way. And there's power in being able to say it multiple ways and know that it means exactly the same thing. Well, you get, if you get 3 different statements, it's going to take 8 rows because you have to have all the possible truths and falses in all the scenarios. If you had 4 statements, P and Q and R and S, then it would take 16 rows. At some point, it's like there are just so many different things involved that this is going to take a long time to verify. So we actually do have some other ways of showing equivalencies and validating truth claims. And I just wanted to show you one more way, and then we'll finish up. So basically, if we prove something, like we proved the law of the contrapositive, or we proved De Morgan's laws with the truth table, now we have those as truths. And once you have some truths, then you can use those to build more truths. So you use the truths that you build with the truth tables as kind of building blocks for more complex things. Maybe if you took a pre-calculus class and you did those trig identity proofs where you started out with some really basic things like tangent x equals sine x over cosine x, and then you built some more complex identities, you kind of get the idea. We start with as few truths as possible, and we try to make them as simple as possible, and then we just build this entire system of thought. In fact, maybe one of the most famous systems of thought, these are called axiomatic systems of reasoning, is Euclid's geometry. So he took these 5 really basic postulates, these 5 assumptions, and he created over 365 truths or theorems from them, which are pretty amazing because his 5 postulates were like, hey, if you have 2 points, you can make a line. If you have 2 points, then there's another point in between them. So he took these really, really basic ideas and he created this monstrosity of truth from them using only logic, which is pretty fantastic. If you ever want to look into it, 13 books of truths, Euclid's Elements, from basically deducing a whole bunch of these theorems from 5 postulates, which is amazing, super cool. So here are some truths. We've proven some of them, like De Morgan's law, but you can actually take these truths and you can create new truths with them instead of going the route of the truth table. And I'll give you an example of one of these here in just a second. But what I'm going to do is I'm going to use a couple of these laws. So this distributive law is pretty interesting. It's kind of like something we've seen in algebra, where if you had like a 3 parentheses x plus 2 or something, maybe you could distribute that in. So it's kind of like if you have a P and, then you can push the P and into this OR statement. So you kind of get this P and Q or P and R. The P and kind of gets distributed. Or you could kind of look at it like, well, look, I got a P and here and I got a P and here. I can actually factor it out and make it look like this. I can pull this P and out in front. So it's a little bit algebraic feeling. Some of the other laws that are interesting. So if I have P and a tautology, that's just the same thing as saying P. That's called identity. It's kind of like almost multiplying by 1. It's interesting. So if I have an OR statement, P or a contradiction, that's the C, then I can just say P, because an OR statement just needs one true thing. And if P is true and contradiction is always false, then you can just say P. This is just unnecessary to say this. So that, like a double negative here, it cancels out. So we've got some interesting laws. We've got, of course, De Morgan's law, which we're familiar with from earlier. There's all these laws, and you can use these laws in proofs of logical equivalencies like this. By the way, that's theorem 2.1.1. Yeah, you might want to go back and pause the video and take a picture of that, because those are really helpful things in proofs, especially ones that get a little more complicated. So here's something that we're going to prove. So we're supposed to prove that all of this in yellow is really the same thing. And I should have had a 3 bar equal sign means logically equivalent. Like this whole thing is really the same thing as saying P. So sometimes you say something in a really complicated fashion and you can reduce what you're saying to something simple. Or I guess you could take something simple and say it in a more complicated way. So let's take a look at what's happening here. Well, right here in this part of it, there's a negation of an and. We know that we can use De Morgan's law. We can kind of push that negation through the and, but the and is going to change into an or, and I'm going to have to negate both of these pieces here. So a negative negative is actually going to undo itself, and that negative negative P is just going to turn into a P. Since I'm pushing the negative in, De Morgan's law forces the and to turn into an or. And then that negative kind of goes over to the Q. So this whole thing right here actually turns into P or not Q. Well, that's interesting. Then if you look carefully here, we've got P or, and over here we've got P or. So the distributive law tells us if we have P and then the same operator or in both places, we can almost like factor it out. It's called the distributive law. So I can take this P or and this P or, I can kind of pull it out, kind of factor out the P or. If you factor out the P or, what's left? Well, what's left is not Q, and I factored out the P or, so Q. So once it's called the distributive law, once I kind of factor out that P or, I've got this not Q and Q. But if you think about that, that's intuitive. You can't have something and its opposite both be true, and that's a contradiction. That's called the negation law. So I replaced this with C, which stands for contradiction. Now I've got P or a contradiction, but we just looked at that. That's really the same thing as saying P. And look, P now matches P. So this is another way to prove logical equivalencies if the statements are kind of complex. And I think it's really fun and really useful. Hey, I hope you enjoyed this lesson. We got some homework problems from the discrete math text, making lots of truth tables. I will see you in the next lesson.